Hello friends, welcome to my channel. Let's have a look at problem 924, minimize malware spread. So in this video, we're going to share a solution based on disjoint set data structure, or union find. So this problem is marked as hard in Leetcode. So actually, if we have the tool of disjoint set data structure, so the logic actually is very straightforward. The problem asks us to return the node that, if it removed, it will minimize the number of infected nodes. So if multiple nodes could be removed to minimize, so we are going to return such a node with the smallest index. So that's the main return requirement from this problem. Actually, the examples given in the problem statement are not very good, in the sense that it does not embody the main logic of this problem. The reason is that, so in example 1, so we have node 0 and node 1 are connected together. But the initial is 0 and 1. Actually, they are belonging to the same connected component or cluster. So we just need to sort this initial and return the first element. So in example 2, it's another extreme. So all the nodes are isolated because this is an identical matrix. In other words, only diagonal elements are 1. So it forms 3 clusters for the nodes 0, 1, and 2. So if we remove any of the node in initial, so it will prevent one node from infection. So we still just need to return the smallest index in the initial list, that is 0. For example 3, it's also an extreme. All the nodes, for all the nodes, there is a edge between any two nodes. So still, we just need to return the smallest nodes in the initial. Also, in the node, in the initial list, the nodes are also a priori sorted. So that actually explains the reason why the examples given here are not very representative. So the constraints about this problem is the following. So n is the length of the graph matrix. So it's a square matrix, so the rows and the columns are same. So the nodes is bounded above by 300 and bounded below by 2. So all the integers in the initial are unique. So that's a consistent assumption in some sense. So with that said, so let's look at the analysis and the method for this problem. So the method is based on disjoint set data structure, and the specific idea and procedure is as follows. First, we're going to partition the nodes, because we have n nodes from 0 to n-1. We partition the nodes to clusters according to connectivity. And the second step is we sort the initial nodes, in other words, all the nodes in the initial list. Then we're going to check for each node to see how many nodes can be prevented from infection if we remove the very node. So lastly, we are going to return the node that produces maximum prevention effect with smallest index. So that's the whole procedure. So one question is how to check atom B in part 2. So this is actually very easy by the observation below. First is that if two indices in the same cluster, so then removing either of them will not reduce infection, right? So this is very straightforward. The second one is that if no other indices in the initial list belong to the same cluster with say the index is I, then the amount of node it can prevent from infection is the cluster size for the cluster it lies in. So this information actually can be easily retrieved from the disjoint set data structure, in other words, from the rack. So in the below implementation, the rack will be the cluster size. So before we look at the code, here is a example we cooked up. So for demonstrating the general logic of the problem, and also a walkthrough. So the graph is made purposely, so it consists of 6 nodes. So the initial is 0, 2, 1, 5. A priori it's not sorted. So the first 2 nodes are connected. Node 2 and node 3 are connected, and node 4 and 5 are connected. So in other words, it forms 3 clusters from the graph matrix. That is 0, 1, one cluster, 2, 3, one cluster, and 4, 5, another cluster. So after we sort the initial list, so we get 0, 1, 2, 5. Then we're going to look at the nodes from left to right. So because their index are in an increasing order now. So 0 and 1 actually belong to the same group or same cluster. So removing either of them will not yield reduced infection. So now if we look at index 2 and index 5, or node 2 and node 5, then removing either of them will prevent 2 nodes from infection. If we remove node 2, so basically node 2 and node 3 are prevented from infection. So similarly, if we remove node 5, then the 2 nodes 4 and 5 are prevented from infection. As we need to return the smaller index, so we're going to return 2 in this example. So with that said, I guess the problem logic is clear, and the procedure we are going to carry out is also clear. So our plan is as follows. So we're going to first implement the DSU class for use. So here, actually, if we want to seek shortcode, actually we can implement the data structure inside the solution method. But here we do not pursue for the shortest code. Rather, we target for natural thought process and succinct logic. So this is the first. The second, we are going to run the procedure specified by part 2 above. So that's our whole plan. Now let's look at the implementations. First, the implementation of DSU. So this actually is very routine now. So I'm going to use a DSU. So the initialization is as this, self. So we're going to use 2 attributes, self roots, which is going to store the node and the parent relationships, the self rex, which is going to store the node and the class size it lies in. So that's the initialization. Now let's look at the find method. For the find method, it accepts 1 additional argument. So here I is the node or the index. That is 0 or 1 up to n-1 in this problem. Here, in order to accelerate a little bit, we're going to implement the find method with path compression. So in fact, it's not absolutely necessary here, but let's do this. First, if I is not in self roots, so we're going to add it to the data structure. So the roots I equals I, self rex equals 1. For this initialization, first the roots I equals itself, because it's an initially isolated node, or it's just a cluster of size 1. That also explains why we set the rec to be 1. Then we're going to return this I. In other case, the I is already in the cluster. Then we're going to retrieve its root. For this, let me introduce a temporary variable called result, whose final state is what we want to return. So also I'm going to initialize a path set, so that we can use path compression. So now it's a while loop. While result does not equal to self roots result. So if this is the case, we're going to add the current state of the result to the set, and then we are going to update the result to be self roots result. Then after this loop, basically we are going to return result. Before the return, let's do a path compression. So for node in path, we're going to set the roots of this node to be the result. So that's it for the find method. So next we're going to implement the unit method. So the unit method accepts 2 additional arguments. So here the I1 and I2 are also the same as in find nodes index. So we're going to find the roots of I1 and I2 to determine if they belong to the same cluster. If not, we're going to reset the roots relation and update the rack. So let's see, root 1, root 2 equals self find I1 self find I2. Then we're going to check if root 1 does not equal to root 2. Then we're going to reset the rack. So let's track the we are going to reset the rack and the root. Let's first track the rack information. If self rack root 1 is greater or equal to that of root 2, then we're going to set the root of root 2 to be root 1, and then we're going to update the rank. So let's copy this and update that. This corresponding to update the cluster size represented by root 1 by that of root 2, because it mimics the merge of 2 different clusters, so the size adds up together. So otherwise we're going to do the same thing but in the reverse direction. Let's copy this 2 lines, and then we're going to set the root of root 1 to be root 2, and then we're going to enlarge the cluster size of root 2 by that of root 1. So that's it for the union function. So now we have finished the implementation of the DSU class. Then we're ready to look at the main logic here. So for that, let me first instantiate the DSU. So DSU. So then we're going to track the length information for convenience for graph. Then we're going to partition the nodes according to connectivity. So essentially we traverse the matrix. So for I in range M, for J in range I plus 1 to M. The reason is that we just need to look at one edge ij, because ij and ji are essentially the same. So then we're going to check if the graph ij if it's 1. So basically we want to union them. DSU union ij. So that's all we want to do. And then we are going to count the roots. So this is an essential step. So roots count. So basically we want to make a counter, collections counter. So we're going to do DSU find I for I in initial. So this way we're going to if two nodes are in the same cluster, then the count of the corresponding roots will be greater than 1. That's one essential observation. So with that said, let's do something also important for the return. So we are going to do a sort for this initial index. The reason is that the list initial is not necessarily sorted a priori. So once we done this, we can prepare for the return. So let's call this one step 1. So DSU and grouping. So after this preparations, so we're going to prepare the return. Let's call this part prepare return. So after we do the sort, actually then we can just need to examine all the nodes in the initial list for node in initial. Let's first do a variable set so that we can make a comparison. So let's call this initial 0, the first node, and assume its cluster size is 0. So we're going to store node and the amount of node it can prevent from infection if deleting. So this is the length or amount. So we want to find the largest amount, right? So we want to find the delegate or the representative of the current node. That is DSU find, right? We're going to find the root, and then if root count of this delegate is greater than 1, so we do nothing, right? Because if you delete that, it does not reduce the number of nodes infected. So we're going to check if this equals 1. Then if DSU ranks, so the rank will check the cluster size, right? So that's an important thing to be noticed. So if this one is greater than info1, then we're going to update this info variable. So to be the node and DSU rex and delegate. So get this information actually is very fast because it's just a dictionary lookup. So once this is done, then we are ready to return. So what we want to return is the info 0. So that's the full solution code for this problem. So let's first do a special case check. Yeah, it passes the example we cooked up. Now let's do a generic case check. Yeah, it passes the generic case. So let's give a quick summary for this video and this solution. So here, first, we implemented a disjoint set data structure with two main methods, find and union. Here, actually, for find, we implement the find with path compression and the union with union by rank. So here, one thing to be noticed is that the rank here is nothing but the cluster size. Then we write the logic for the problem. We split this solution to be two parts. First, we instantiate the DSU data structure and do the grouping or clustering. So after that, we do a roots count, right? So finally, we check each node after we sorting the initial list, and then prepare the output. And finally, we return the corresponding node information. So that's all about this solution and this video. So if you find it interesting, so you are welcome to share with your friends, or you can check out other videos in this playlist or in this channel. Thank you very much.